It's a pleasure and honor to be here celebrating Philippe's birthday. I honestly can't remember where or when I met Philippe, but I had met you by 2008 because I remember specifically making an effort to attend this Schrödinger Institute program because I found your lectures very inspiring, very fun. And one of Philippe's favorite objects is plane partitions, so I chose my topic today to touch on some related things. So I'll be telling you about something called the magic number conjecture for the amplituhedron, and this talk is based on joint work with Matteo Parisi, Melissa Sherman-Bennett, and Ron Tesler. Okay, so let me give you an outline of my talk. I'm going to first tell you about something completely combinatorial, partial cyclic orders and tricolored subdivisions, as well as some related polytopes. And after telling you this completely combinatorial story, I'm going to switch gears entirely and tell you a bit about the amplituhedron and the magic number conjecture for the amplituhedron. And at the end, I'll explain how these two seemingly different stories are actually related. Okay. All right, so first let me tell you what is a partial cyclic order. So this is an analog of a poset, but it's a circular analog of a poset. So a partial cyclic order on a finite set X is a ternary relation. So this is subsets of triples such that for all A, B, C, and D in your set X, if A, B, and C is a triple, then so is CAB. So we're talking about a cyclic order. If ABC is in your collection of triples, then CBA is not. And then there's a transitivity property as well. So this is a cyclic analog of the notion of poset. And so, for example, if you give me some triples, 2, 5, 7, 5, 7, 6, 1, 8, 7, and 8, 7, 2, this determines a partial cyclic order on the set 1 through 8. And I haven't written out all triples in that partial cyclic order, but for example, the fact that 2, 5, 7 is one of my triples means that 5, 7, 2 is also one of my triples, and so is 7, 2, 5. And then we say that a cyclic order is total if for all A, B, C in my set, either A, B, C is a triple or A, C, B is a triple. So informally, a total cyclic order on 1 through n is a way of placing the numbers 1 through n on a circle. I feel like I'm being tested in some way. Okay, so a total cyclic order on 1 through n is a way of placing the numbers 1 through n on a circle, just as a total order is a way of placing 1 through n on a line. Okay, so that's the notion of partial cyclic order. And now let me introduce a combinatorial object. So this is a tricolored subdivision of an n-gon. And so what we have here, I've cut up my polygon into smaller polygons, and they all have a color, either black, gray, or white, in which every edge connects two vertices of the n-gon. Oh. So you think it's a Zoom thing? No? The mic, oh. Not sure. Okay, looks like I should go back to full screen mode, yes? Yes. Okay. All right. Okay, so this tricolored subdivision is just a way of chopping up our polygon into smaller polygons, and there's 3 colors. And so from every such tricolored subdivision tau, we can read off a cyclic order. So how do we do that? So I'm going to read vertices of all of the white polygons clockwise. So I have a white polygon here with labels 2, 5, 7 when I read them clockwise, so I will record that. And I will also read vertices of black polygons counterclockwise. So 5, 7, 6, for example, or 1, 8, 7, 2. And I'm going to ignore all of the gray polygons. And so this particular tricolored subdivision requires that 2, 5, 7 and 576 and 1872 are circularly ordered. And then a circular extension of my partial cyclic order is just a total circular order that's compatible with my partial cyclic order. So for example, here, given my partial cyclic order, which was to require that 257 is in order, 576 and 1872 are in order, one possible total circular order compatible with that would be the following list. So I see 2, 5, and 7 in order, so this is satisfied. I see 5, 7, and 6 in order, so this is satisfied. And then I see 1, 8, 7 wrap around to 2. Those are in order, and so this is a circular extension. Okay, all right, so now I want to use this. Oh.
Not telling more on that. There is a graphical way of understanding which circular extension are. I was guessing, given that this polygon is a polygon, that there was a graphical way of constructing the circular extensions, or there is no graphical way of knowing.
I don't know a graphical way to construct all of them.
It is worth searching.
Maybe. Well, yeah, maybe we can talk afterwards. So next, what I wanted to do was tell you how to use this.
So 3 and 4 can be in any order?
Yes. So with the gray polygons, that's just there to say I don't care what order they're in. Yeah. Okay. So now I want to use this combinatorics to write down some identities in Plücker coordinates. Okay. All right, so just a review of notation. The Grassmannian GRKN is the set of all k-dimensional subspaces in an n-dimensional vector space. I'll represent an element by a full rank k by n matrix. So here k is 2, n is 4, and the row span here represents a 2-plane in 4 space. And now if I is a k element subset of 1 through n, then the Plücker coordinate p sub I of c is the minor, it's the determinant of the k by k submatrix located in column set I. So my Plücker coordinate in columns 3 and 4, my Plücker coordinate p3, 4 would be 0 plus 6. Okay. All right, so now I'm going to write down some identities using these tricolored subdivisions. So if you give me a permutation, W, which is I'll write as a list of numbers, W1 through Wn, we can define what's called a Park-Taylor function, Pt of W, and it's 1 divided by a product of a bunch of Plücker coordinates. These are Plücker coordinates for the Grassmannian of 2 planes in n space, so indexed by 2 element subsets. So this is the Plücker coordinate P W1, W2, times the Plücker coordinate P W2, W3, and so on, and I wrap around all the way to P Wn, W1. So this is some rational function on the Grassmannian of 2 planes in n space. And now we have a little identity. Uh-huh.
Is P12 equal to P21?
Good question. I will think of these as anti-symmetric. So P12 will be the negative of P21. Yeah. Okay. So now we get an identity. So let tau be a tricolored subdivision with at least 1 gray polygon. Now, I said in the very beginning of this talk how you can read off from it a cyclic partial order. And now the statement is that if I sum up the Park-Taylor functions over all circular extensions of that cyclic partial order, then I get 0. Mm-hmm.
So why do you say the cyclic partial order? Aren't there several?
So given 1 tricolored subdivision, I get 1 cyclic partial order, which is the...
But I thought if you have a gray polygon, then things don't matter.
Oh, that means I'm imposing no condition in my partial circular order. So the...
Okay.
Right, so the...
There is an order here between 3 and 4 on the bottom.
So this is one of multiple circular extensions of the partial order. So there's a whole, so just like there's many linear extensions of a poset.
There's circular extension and circular order.
Right. Okay. Okay, good. So given a tricolored subdivision with at least one gray polygon, we get a cyclic partial order, which will have multiple, in general, circular extensions. And if you look at all of those circular extensions and you sum up the Park-Taylor functions, you get 0. Okay, so that's an identity. And I'll just show you the very simplest example. Here is a tricolored subdivision of a square. It has one gray polygon. And this combinatorics forces, because I see a white polygon, I want to see 1, 2, 3 appearing in order. And the total circular orders in which 1, 2, 3 appear in order are the circular order 1, 2, 3, 4, 1, 2, 4, 3, and 1, 4, 2, 3. These are all 3 total circular orders in which 1, 2, and 3 appear in order. And now the theorem says that this sum of Park-Taylor functions is 0. So this Park-Taylor function is coming from this, right? I'm forming the Plücker coordinate P12, then P23, then P34, then P41, and that gives me this. This one gives me this Park-Taylor function. I see 1, 2, then 2, 4, then 4, 3, then 3, 1. And this Park-Taylor function comes here. And if you take this identity and you clear denominators, you will get exactly the 3-term Plücker relation. Okay, so, all right, any questions?
So is it always as simple as this? Maybe that if you clear denominators, then you get a Plücker relation?
No. I wouldn't know how to classify all such things, but all such things you can obtain using a combination of Plücker relations, but you in general will get something more complicated. Yeah. Okay. All right. So just a little bit of context. These Park-Taylor functions have appeared before, related to M0n and scattering equations, related to Lie polynomials, related to non-planar Plebit graphs. And many of the identities that we get are well-known identities from physics called the U of 1 decoupling identity and the Shuffle identity. And interestingly, there's some analogous results for linear extensions of posets due to an old paper of Curtis Green in connection to the Murnaghan-Nakayama formula. So anyway, so there's some history behind such things. And now I want to explain how to go from a tricolored subdivision to a polytope. Okay, so changing gears a little bit. So from such a tricolored subdivision, I can associate a polytope. And maybe the definition of the polytope is not so terribly important, but I'll just say that for any arc, compatible arc in this polygon, from I to j, with I less than j, we get some kind of inequality like this, where xi plus 1 plus ... plus xj minus 1 is bounded below and above. And, okay, I think the definition is easy enough. Compatible arc is an edge of a polygon or must lie entirely inside a black or a white polygon. And the area statistic that is the upper and lower bound is something simple where you're counting basically how much black stuff is to the left of your arc or how much black and gray stuff is to the left. So anyway, so there's a simple polytope that we can write down associated to every such tricolored subdivision. It's going to be some polytope lying inside of a cube.
So area is number of points or is true area?
Okay, so I'll tell you exactly what area is. So if I take the arc, say 1 to 7, what I'm going to do to count the area is I'm going to count how much black stuff is to the left of the arc 1 to 7. And if I triangulate the black stuff into triangles, I'll see one black triangle here, 1, 2, 7, and I will also see this other black triangle here.
Okay,
So
number
area
of
will be
triangles
2.
in a saturated triangulation.
Yes. Yeah. Okay, so we have a simple description of a polytope associated to any tricolored subdivision. And so now from a tricolored subdivision, we've constructed two things, a partial cyclic order and also a polytope. And so a theorem is that for any tricolored subdivision, our polytope has a triangulation into unit simplices labeled by the circular extensions of the partial cyclic order. And so in particular, the volume of our polytope equals the number of circular extensions. So this is the statement again. And there's been work that's related to this. So for example, first of all, there's an old result of Richard Stanley that the volume of the order polytope of a poset equals the number of linear extensions of P. Okay, so that's kind of a classical work from maybe the 1990s. And also there's been other related work of Ayer, Jossuet Verge, and Ramasamy, and also Gonzalez, De Leon, Hanusa, Morales, and Yip. And both of these sets of authors worked in two slightly different contexts, but also introduced a set of polytopes whose volume was counted by the number of circular extensions of a cyclic partial order. Okay, so none of these settings are exactly the same, and there's some overlap, but not a whole lot. But in all three cases, it's a volume of a polytope being counted by the number of circular extensions of a poset, of a partial circular order. And I'll just mention that work of my student, Yuhan Zheng, is upgrading our result here to a formula for the H star vector. Okay, so this was the kind of combinatorial bit that I wanted to explain before I switch gears and talk about the amplituhedron. Okay, so to introduce the amplituhedron, I have to remind you of the Grassmannian and its Plücker coordinates. And to any element in the Grassmannian, we have an associated matroid. So this is just the data of which Plücker coordinates are non-zero. So given any element in the Grassmannian, I can read off which k-element subsets index a non-zero Plücker coordinate, and that data is called the matroid. And classical work of Gelfand, Goreski, McPherson, and Serganova introduced the matroid stratification of the Grassmannian. So what they did was consider the subset of the Grassmannian. So given a collection of k-element subsets of 1 through n, they considered the subset of the Grassmannian where your Plücker coordinate is non-zero if and only if I lies in your collection. So that's called a matroid stratum. And this gives a decomposition of the Grassmannian into these matroid strata. Now, it was quickly realized that the topology of these strata is very bad. That's Mignof's universality theorem. But there's a very nice positive analog of all of this work. So starting in the 1990s, Lustig introduced total positivity for partial flag varieties. And this was developed by Reach, and in the Grassmannian setting by Postnikov. And so what we do now is we look at the subset of the Grassmannian where our Plücker coordinates are all non-negative. Or if you're worried about the fact that they're projective coordinates, just require that all Plücker coordinates have the same sign. Okay? So I think this positive Grassmannian came up in Rick's talk the other day. So inspired by this matroid stratification, you can partition the non-negative Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are zero. So we can do the same thing as before. M's a collection of k-element subsets of 1 through n, and we look at the subset of the non-negative Grassmannian now, where our Plücker coordinate is strictly positive if and only if I lies in our collection, and otherwise will be zero. And now, in contrast to the terrible topology of the matroid strata, the topology of these positive strata is as nice as possible. So if SM is non-empty, then it'll actually be a topological cell, homeomorphic to an open ball. And so we have a cell decomposition of the totally non-negative Grassmannian into these positroid cells. and there was a lot of beautiful work after this. In particular, Postnikov has a nice classification of all the cells. And now I want to explain how this then led to the definition of something called the amplituhedron. So the amplituhedron is a geometric object indexed by 3 positive numbers, n, k, and m, plus a matrix Z. And it was defined by Arkani, Hamed, and Trinka, 2 physicists, in 2013. And I'll give you the definition, and then I'll tell you some of the context. Okay, so we have our positive numbers n, k, and m. And we also fix a matrix Z, which is an n by k plus m matrix with positive maximal minors. And we use this matrix Z to define a map. Okay, and this map is it's a map from the non-negative Grassmannian of k-planes in n space into the Grassmannian of k-planes in k plus m space. And this map is really, really easy. It's simply matrix multiplication. So take your k by n matrix here, multiply it by Z. So Z was n by k plus m, so the matrix product is k by k plus m. And there's a lemma that k by k plus m matrix is full rank, and hence gives an element of the Grassmannian of k-planes in k plus m space. Okay, so that's a map that I'll call the amplituhedron map. And now the amplituhedron is the image of the totally non-negative Grassmannian under this map. So it's a subset of the Grassmannian of k-planes in k plus m space. Okay, so this definition, like when I first saw this definition, I thought it was really kind of weird. But I hope I will convince you in the next few minutes that it's actually a very, very interesting object. Okay, so let me just say a little bit about the motivation. The motivation comes from n equals 4 super Yang-Mills. And there was this very important recurrence of Brito, Cacciazzo, Fang, and Witten that expresses scattering amplitudes as sums of rational functions of momenta. So it's a sum of rational terms, and the individual terms had spurious poles. Singularity is not present when you sum everything up. And then in 2009, Andrew Hodges observed that in some cases, the amplitude being computed was actually the volume of a polytope, and the spurious poles arose from internal boundaries of a triangulation of the polytope. So to say this again, in the small examples Hodges looked at, he could express the amplitude as the volume of a polytope, which was being cut up into triangles, into simplices. There was one rational term for every simplex, and the poles were coming from all the boundaries of the simplices. And so the poles that were getting canceled out came from internal boundaries of simplices that were meeting. Okay, so Hodges observed this in small examples and asked if in general you can express the amplitude as the volume of some geometric object. And so that was the motivation of Arkani, Hamed, and Trinka, who found the amplituhedron as the answer, at least the conjectural answer, to this question. And their evidence was that they could interpret this BCFW recurrence as giving a kind of triangulation of the amplituhedron. Okay. Any questions? So this is kind of like the high level overview. Now, this was hailed by Wired magazine as a jewel at the heart of quantum physics, and was also featured as number 10 among the 100 top stories of 2013 by Discover magazine. So these particular physicists seem to be extremely good at advertising their geometric objects to lay people. I'm not quite sure how they managed, but anyway, this is some kind of artist rendition of amplituhedron. Okay, all right, but okay. So this is just a review of the definition, and now I also want to convince you this is interesting by showing you how in special cases the amplituhedron is a nice mathematical object. Okay, so a sort of boring case. If m equals n minus k and this amplituhedron map is invertible, then you just recover the totally non-negative Grassmannian. If k equals 1 and m equals 2, a small computation will convince you that the amplituhedron is really just equivalent to an n-gon viewed in projective space. If k is 1 and m is general, and n is also general, you get a cyclic polytope in projective space. And if m is 1 and k and n are general, you get the bounded complex of a cyclic hyperplane arrangement. So, okay. So anyway, so in special cases, the amplituhedron recovers a nice object. Okay. So back to the original motivation of the amplituhedron, we want to understand how to triangulate it or cut it up into pieces to understand the amplitude. So recall that we have this decomposition of the non-negative Grassmannian as a cell complex, and we have a map from the totally non-negative Grassmannian onto the amplituhedron. So this is a continuous surjective map, and it's I want to emphasize it's in general surjective, but very far from injective, because the dimension of this non-negative Grassmannian is k times n minus k. The dimension of this amplituhedron is k times m, and based on our choice of parameters, in general, this dimension is smaller than this dimension. Okay. So how do we want to triangulate it or tile it? So what we're going to do is we're going to try to understand this km dimensional object by using km dimensional cells from the domain. Okay, we don't want this highly surjective map. Instead, we want to use same dimensional pieces in the domain whose images map injectively, are injective images. Okay, so a tiling of the amplituhedron is going to be a collection of closures of images of km dimensional cells here, such that our amplituhedron map is injective on all cells we've chosen. And I'll express that by saying that the image of the cell is a tile. We also want the union of tiles to equal the amplituhedron. And we also want the interiors of tiles to be pairwise disjoint. Okay, so I want to chop up this amplituhedron by using same dimensional cells over here, which map injectively, whose unions cover the whole thing, and whose images are disjoint. Okay, and again, the motivation is that the volume of the amplituhedron computes scattering amplitudes, and the original conjecture from the first paper was that certain BCFW cells, so certain cells over here, give a tiling of the amplituhedron. And I should say the case of most physical interest is m equals 4, but they introduced the amplituhedron for any m. So I'll just mention that this original conjecture of Arcani, Hammett, and Trinka has by now been proved, first for a kind of standard tiling by Evans, O'Hara, Leclerc, and Tesler, and then for all BCFW tilings by them together with Matteo, Melissa, and I. And this result actually heavily involved cluster algebras. But anyway, that's not what I'm going to talk about today. Instead, I want to tell you about the combinatorics of tilings. Okay, so back in maybe 2017, I was looking at tilings of the amplituhedron together with Stephen Karp, my then student, and Yan Zhang, and we were looking at numerology of tilings for all the different cases of amplituhedra that we could compute or that had been computed. And so we made this little table. So maybe the interesting numbers here are that when m is 1, any tiling of the m equals 1 amplituhedron always uses exactly n minus 1, uses n minus 1 choose k tiles. When m equals 2, the tilings of the amplituhedron had size n minus 2 choose k. When m equals 4, the then conjectured tilings of the amplituhedron had this cardinality, which is a Neriana number. And when k is 1 and m is even, the amplituhedron is a cyclic polytope, and it's well known that all tilings of an even dimensional cyclic polytope have this cardinality. Okay, so we compiled this table of numbers and tried to guess the generalization. And we observe that the generalization is this number of McMahon plane partitions. So, if you let capital M of ABC be this number, this famous product formula, then all known tilings of the amplitude for even M have cardinality M of K, comma N minus K minus M, comma M over 2. Okay, so we'll call this prediction, the prediction that tilings should have that size, the magic number conjecture. Okay, so this generalized the numbers on the previous slide, and yeah, and I'll just mention these numbers are very well known, and they count plane partitions, they count non-crossing lattice paths, they count rhombic tilings, they count perfect matchings. So this is a really beautiful combinatorial number. And in my figure here, A, B, and C are 2, 4, and 3. So like this here is a plane partition. You can think of it as a plane partition fitting inside a 2 by 4 by 3 box. Okay, any questions? Okay. All right, so then what we proved is that the magic number conjecture is true when M equals 2. So if you look at the amplituhedron for M equals 2, the tilings always have size, this number of plane partitions in a K by N minus K minus 2 by 1 rectangle, which is the binomial coefficient N minus 2 choose K. And as a sanity check, if K equals 1, the amplituhedron recovers an n-gon, a polygon, and our theorem says that all triangulations of an n-gon have size n minus 2. So this is probably the most complicated proof ever written that triangulations of a polygon have size n minus 2. Okay, all right, but fortunately our theorem is more general than this because it works for any K. Okay, so let me just say a little bit about the ideas that go into the proof. And maybe I should first tell you the sort of idea that's wrong but gives you a hint as to what one should do. So if you had some polytope, you were trying to show that all of its triangulations had the same size, if you were able to classify all simplices that can occur in a triangulation, and if you furthermore proved that the volume of any simplex that you can put inside this polytope had volume equal to, 3 or something, that would tell you automatically that all tilings must have the same size. Right? If all of your simplices have the same volume, the volume of your whole polytope is constant, and so therefore any triangulation of your polytope would have to have the same size. So that's kind of the rough idea, but it has to be adjusted a little bit. Okay, but the first step is basically the same as what I suggested. The first thing you have to do is classify all of the tiles for the M equals 2 amplituhedron. Okay, so that's step one, and that's something that we had done already using bicolored subdivisions. Okay, and just as every Park-Taylor polytope has a decomposition into simplices, where W ranges over circular extensions, what we do is show that every tile for the M equals 2 amplituhedron has a decomposition into something like simplices labeled by permutations W, which range over certain circular extensions. And then what we do after classifying our tiles as unions of W simplices is we define a certain invariant of a tile, we define a certain Park-Taylor function of a tile, and we show that this function is the same for every single tile. And so that shows that tilings of our M equals 2 amplituhedron always have the same size. And just as a small aside, the total number of chambers into which we decompose the amplituhedron is equal to the Eulerian number. So there's a lot of nice permutation combinatorics that comes up. Okay. Any questions? Uh-huh.
Question. Is there a natural grading of amplitude that leads to Q enumeration?
Oh, that's a great question. And I did look at that. I have not been able to find such a Q grading, at least yet. But yeah, it would be really nice if one could put in the Q. Yeah. Uh-huh.
So by classification of tiles, do you mean the matroids which contribute, like in this image, is non-zero?
Yes. So yes, actually, the next slide will say exactly what's the classification, and it will be. So what we do is we classify exactly the 2m dimensional cells of the non-negative Grassmannian, which map injectively to the m equals 2 amplituhedron. I don't know if I answered your question. Did that answer your question?
Yes.
Okay.
So you have some structure for the box plane partitions. It has a poset structure.
Right.
Can you label individually each tile by a plane partition, or is it just that they are equinumerous?
So far they're just equinumerous, and it's a little confusing also because there are many tilings for the m equals 2 amplituhedron, and one of them looks particularly nice, and then it looks a bit like adjacency of tiles is related to the poset structure, but not exactly. Not exactly. Yeah. Okay. Let's see. How much time do I have?
5 minutes.
5 minutes. Okay. All right. So so in this next slide, I was going to say exactly what is the classification of tiles for the m equals 2 amplituhedron. This will also use Castelline matrices, which have come up in a couple earlier talks. So the tiles for the m equals 2 amplituhedron. So these are the cells. These are the cells over here which have the right dimension and which map injectively to the m equals 2 amplituhedron. So these tiles are in bijection with bicolored subdivisions of an n-gon with total area k. So I'll just show you an example how that works. So this is what I would do if I wanted to construct a cell over here which mapped injectively to the amplituhedron and had top dimension. So what we would do is I would choose a triangulation. I would take a bicolored subdivision of an n-gon. So this is meant to have black and white polygons, although my black looks a little gray here. So I'll take my my bicolored subdivision, and I will triangulate these black polygons into k black triangles. And I can choose any black triangulation. Then I will put a white vertex in every black triangle connected to the 3 external vertices. And now how to build my cell here, I'm just going to write down the k by n Castellan matrices with rows and columns indexed by the white and black vertices here. So here I started with my bicolored subdivision, and it has area 5, because when I chop up the black into triangles, I have 5 black triangles. So my rows are indexed, there's 5 rows, and there's 9 columns. 9 is for the 9 of my 9-gon. And this first row here, you can think of as 7, 8, 9, is like the fact that this white vertex here is incident to 7, 8, and 9. And this row here is, its support is 1, 7, and 9, and that's coming from this triangle over here. Okay, so what I'm saying is that, so imagine this star is secretly a copy of R plus, or R minus, there's some sign conventions. So if you range over all such matrices like this, you get a cell in the totally non-negative part of G5, 9, which maps injectively to the amplituhedron and has top dimension. Okay, so this is the classification of tiles. So these are what we use to tile our amplituhedron. Okay, and then maybe I don't want to go into details here, but there's certain coordinates that you want to use to talk about the amplituhedron, and you use these coordinates to partition the amplituhedron and its tiles into chambers that are a bit like simplices. And at the end of the day, you define an invariant associated to every tile and show that the invariant associated to every tile is always the same constant. It's going to be -1 to the k times a Park-Taylor function. Okay, and so because we show that every single tile gets the same invariant associated to it, that implies that all tilings must have the same cardinality. And there was one known tiling consisting of n-2 choose k tiles, and so now all tilings must have that same cardinality. Okay, so so thanks a lot. These are the main references, and happy birthday, Philippe.
We have time for a few questions, I think.
Thank you very much for the talk. So at the beginning, you had these tricolored subdivisions, and at the end, you are labeling your tiles by bicolored ones for A and K2.
That's
Do you
right.
expect tricolored subdivisions to show up for other amplituhedra?
Yeah, that's a great question. So the K, right. So for the amplituhedra, we only have the bicolored subdivisions, and the number of black triangles was this K statistic. Was this K statistic in the amplituhedron, which is the K in the GKN. The only reason we worked with tricolored subdivisions when writing down the polytopes and the identities was that we realized we could get a more general class of cyclic partial order, more general class of polytopes. And then we could get identities that had the form sum of Park-Taylors equals 0 instead of identities of the form sum of Park-Taylors is -1 to the k times something else. Yeah, so that was just combinatorially inspired to go to be more general for the combinatorics. But for the amplituhedron cares about these two colors, and the black triangles is the K from GKN.
So what will they show up for higher n?
Sorry? For higher M, there is no known classification of tiles. I mean, we've certainly looked for M equals 4, but we do not have a classification. And in general, the combinatorics gets significantly harder when you go to higher M. Yeah. We know some things. We know many tiles for M equals 4, but we don't have a classification. And like, if you look at the numerology, it doesn't have a nice, it doesn't show up in OEIS, but number of tiles for M equals 2 does show up in OEIS. So, yeah.
Were there cyclic orders appearing in this last part?
Yeah, so that was the part that I kind of decided to breeze through. So basically, what we do, so let me just tell you the analogy. A tile of the amplituhedron in this setting is very much like one of our Park-Taylor polytopes, and it can be chopped up into these pieces that are analogous to simplices that we called chambers. And we classified what chambers appear in every tile, and the chambers that appeared in every tile were exactly labeled by permutations which were circular extensions of a partial cyclic order. Yeah.
I didn't understand what you learned from this triangulation tiling as far as the scattering amplitudes are concerned. Do they have simpler analytic properties or what?
Well, so I guess what we learned for the M equals 2 amplituhedron is that all ways that you can write your scattering amplitude as a sum of rational functions will always have n-2 choose k terms. I'm not sure that physicists would care about that, to be honest. As an enumerative combinatorialist, I'm happy with such a statement, but I'm not sure if physicists would care whether their formulas have n-2 choose k terms or some other number.
Okay, and going beyond m equal 2 seems out of reach.
So, I mean, there's a lot of stuff that we can do for m equals 4. So we did prove this original conjecture of Arcani, Hamid, and Trinka that the conjectural tilings that explained the BCFW recurrence for scattering amplitudes were really tilings for the amplituhedron. So in a sense, the original kind of, so when the amplituhedron was first introduced, the idea was that it should provide a geometric framework to understand the BCFW recurrence. But that was conjectural at the time, and now that's been proved. But the more refined combinatorial statements, like all tilings have the same size, so far we don't know how to do that for higher M.
Okay, so thank you again very much.